Prove the statements in 1 through 11. In each case, use only the definitions of the terms and the assumptions listed on page 161, not any previously established properties of odd and even integers. Follow the directions given in this section for writing proofs of universal statements. The statement we have to prove is, if an integer greater than 4 is a perfect square, then the immediately preceding integer is not prime. We start our proof with the word proof. The first sentence is going to be our assumption, which is the premise of this conditional statement. So this conditional statement makes a universal claim about all integers greater than 4 that are perfect squares. So we're going to instantiate an arbitrary but fixed integer greater than 4 that is a perfect square. We'll start off by saying let n be an integer with n being greater than 4 and n is a perfect square. So because n is an arbitrary but fixed and instantiated integer with the following properties, that n is greater than 4 and n is a perfect square, the thing we need to show is that for this arbitrary but fixed integer n that we instantiated, the immediately preceding integer n minus 1 is not prime. So our goal is to show that n minus 1 is not prime. And this is the assumption that we get to work with. We could start by unpacking what it means to be a perfect square. So by definition of a perfect square, n equals k squared for some integer k. So this is the point where I can see a lot of students getting stuck, because we've taken our assumptions and we've unpacked the definitions within our assumption. But now the question is, where do we go from here? Well, the conclusion of the statement is that the immediately preceding integer is not a prime. So what is the immediately preceding integer of n? Well, that would be n minus 1. We can clarify that k is positive since n is positive. Now, it might be the case that negative k is also a solution to this, but we want to take the positive solution. So we're going to assume that k is positive. Now, we might notice that n minus 1, which is the immediately preceding integer, is the same thing as k squared minus 1. And that's because n is the same thing as k squared. So we can substitute n with k squared. Also, we can say that k squared minus 1 is factorable. So k squared minus 1 is equal to k minus 1 times k plus 1. And this is a basic rule of algebra. So now we've taken the immediately preceding integer and we've represented it by this number k minus 1 times this number k plus 1. Both of these numbers are integers since k is some positive integer. But in order for the immediately preceding integer to not be prime, we need to make sure that neither of these factors is equal to n minus 1. So we could say that since n is greater than 4 and n equals k squared, then k squared is greater than 4, and that's by substitution. Now, since k squared is greater than 4, we could say that k is greater than 2. Since the next smallest perfect square that's greater than 4 is 9, that means k has to be at least 3. Now, since k is greater than 2, then k minus 1 would be greater than 1 by subtracting 1 on both sides. And k plus 1 would also be greater than 1, since it would be greater than 3 if we added 1 to both sides. So k plus 1 is greater than 3, which is also greater than 1. And this is all by algebra. So now we've shown that k squared minus 1, which is the same thing as the immediately preceding integer n minus 1, which is k squared minus 1, is equal to some positive integer k minus 1 times some other positive integer that's k plus 1. Both of these integers are greater than 1, which means that k squared minus 1 is a composite integer. Let's take a look at what it means for an integer to be composite. An integer n is composite if and only if n is greater than 1 and n equals rs for some integers r and s, with r being greater than 1 and less than n, and s being greater than 1 and less than n. Now, since n equals k squared and n is greater than 4, we could say that k is less than n. And this is again by algebra. So we rearrange n minus 1 into these two numbers k minus 1 and k plus 1. Both of these numbers are less than n minus 1 since n is the square of k and n is greater than 4. We also know that k minus 1 and k plus 1 are both greater than 1, which means by definition of a composite number, n minus 1 is a composite number, which means that n minus 1 is not a prime number. Now, the only flaw with this proof, I would say, is that we didn't explicitly show that k-1 is less than n-1 and that k+1 is less than n-1. But I don't think that really requires justification here, since n is greater than 4 and n equals k squared. And so that means k is at least 2 smaller than n. Now, we didn't really justify that k-1 and k+1 were both less than n-1, and I think you can improve that proof by justifying that claim. However, I think what's important here is that we've proven that this integer n-1 is not a prime, since we have two factors k-1 and k+1, neither of which is equal to n-1. And so that means that this integer n-1 is not prime. I don't think this part of the definition is necessary for the composite number. Thanks everyone, and I'll see you in the next video.